Okay, so my theoretical computer science assignment is on graph theory. Just like the name would suggest, it is the study of graphs. However, they are not graphs in the traditional sense. It is not a geometric representation of a function on the Cartesian plane. Rather, graphs in this context are mathematical structures used to model relations between objects. They are made up of nodes and connected by edges. You can consider them to be the ordered pair G is equal to VE, where V represents a vertice or a node, and E the edge connecting that node or any two nodes to each other. A graph may be undirected, meaning that there is no distinction between the two vertices associated with each edge, or it can be directed, where the edges have a direction associated with them. Each edge can also have weight. This is just a numerical value assigned to an edge, and one can think of it as the cost of traversing that edge. This concept is quite useful, and I will explain why later. So assume that we have these numbers here, and going from A to D would just cost 5, A to E 10, and so on and so forth. Graphs in general have many applications in a multitude of fields, including computer science, physics, mathematics, and biology. They can be used to represent and simulate many things, including social networks and electronic circuits. A simple graph without cycles is known as a tree and looks like this. And this is just a picture from one of my favorite movies, Good Will Hunting, and the problem that he's solving here actually has to do with trees. I use the word cycle in my definition of a tree, and essentially the cycle is just a sequence of distinctive adjacent vertices that begins and ends at the same vertex. Furthermore, a simple graph that contains every possible edge between all the vertices is called a complete graph. The way that graph theory emerged as a field was quite interesting. Initially, there was a paper written by Leonhard Euler on the seven bridges of Königsberg, which was published in 1736. This is regarded as the first paper written about graph theory. The city of Königsberg in Prussia, present-day Russia, was set on both sides of the Pregel River and included two large islands which were connected to each other or to the two mainland portions of the city by seven bridges. The problem was to devise a walk through the city that would cross each of those bridges once and only once. Euler proved that the problem has no solution. Through doing so, Euler actually devised a new formula known as Euler's formula, relating the number of edges, vertices, and faces of a convex polyhedron, which was later studied by Cauchy. And this actually represents the beginnings of the branch of mathematics known as topology. Topology is a very interesting topic in pure mathematics, and I would like to use it as an example to describe some key concepts in graph theory. In fact, there's even a branch of mathematics known as topological graph theory, which further highlights the interconnectedness of the two fields. So, in particular, I would like to explore one of the most famous algorithms in computer science, being Dijkstra's algorithm. Dijkstra's algorithm is an algorithm for finding the shortest path between nodes in a graph, which may represent, for example, road networks. The algorithm itself I won't detail here, but it is fairly straightforward, yet incredibly powerful. And this is actually where the concept of weight comes back. The algorithm uses this concept to dictate which path it should take depending on the cost associated with the edge. So assume we start at node A and we would like to go to an arbitrary node. We use these numerical values associated with each edge to find the most efficient path. Now, the starting node starts at 0, and the node that is unvisited has a value of infinity. And I use this here to just represent that this actually does have a computer science implementation in a multitude of different languages, including Java, C#, C++, Python. So it is very prevalent in the computer science industry and world. So you may be asking, what exactly does it have to do with pure mathematics? Well, suppose that we are studying traffic networks and would like to optimize them. This problem is known as Brace's paradox. We can create, actually, a graph-theoretic structure out of a traffic system and treat the flow of traffic as a strategic, non-cooperative game. Each road can be an edge connected by nodes, and we can have players in this graph taking the paths which have the least cost associated with them. And in game theory, which is actually very frequently studied with graph theory, there's this concept of Nash equilibrium. Nash equilibrium is simply a state in the game in which no player can gain anything by changing their strategy. Well, in this graph theoretic structure, it turns out that there is actually a theorem in topology which allows us to find the Nash equilibrium of a system, and it is known as Brouwer's fixed point theorem. It states that a continuous function from an n-ball to another n-ball must have a fixed point. Now that might sound quite abstract and convoluted, but simply if we were to treat the strategies of the players on a graph as a point on a simplex, the fixed point on that simplex would be the Nash equilibrium. A simplex is simply a higher dimensional generalization of a tetrahedron or a triangle. In this case, we would obviously be dealing with a 2 simplex, as we are dealing with 2 dimensions, and it goes all the way up to n dimensions, and as you get increasingly further, it gets a lot more complicated, as you can see. This actually demonstrates how graph theory can have many applications both in an abstract and a practical sense, and I think that this result with Brouwer's fixed point theorem is particularly, interesting and astounding, to say the least. Another cool thing that we can do with graphs is represent them as matrices. The matrix representation of a graph is known as its Laplacian matrix. Assume that we have a simple graph G with n vertices. Its Laplacian matrix is defined as L is equal to D minus A. D is the degree matrix and A is the adjacency matrix of the graph. Since G is a simple graph, A only contains ones or zeros and its diagonal elements are all zeros. Here's an example of a simple labeled undirected graph and its Laplacian matrix. So here we have this, we have the degree matrix, which is, again, it's just the number of edges coming out of that node. So on this first column, the first node only has 2 edges coming from it. Let's go to number 2. It has 3 nodes coming. Hence, we have 3 here, and so on. And you can just generalize that to all the nodes. The adjacency matrix simply is used to denote whether 2 nodes are adjacent. A 0 representing that they are not adjacent, and 1 representing that they are adjacent. And once we subtract these 2 matrices, we actually have a Laplacian matrix, which is right here. The Laplacian matrix can be useful in many different applications, and it has many useful properties. Together with Kirchhoff's theorem, it can be used to calculate the number of spanning trees for a given graph. So, moving on to some of the key developments in graph theory, most of them are actually concerning solutions to long-standing problems in the field that, if they were to be solved, would have significant impacts on our understanding of graphs. It is also important to note that many of them have already been solved. Such problems include the traveling salesman problem, the shortest path problem, and the Steiner tree problem, amongst many, many more. There's also an interesting subtopic of graph theory called graph coloring, which also has its plethora of problems and theorems, including the 4-color theorem and the strong perfect graph theorem. Typically, one is interested in coloring a graph so that no 2 adjacent vertices have the same color, or with other similar restrictions. One may also consider coloring edges, possibly so that no 2 coincident edges are the same color, or other variations. Furthermore, there are many applications in graph theory that have proliferated across the academic spectrum in recent years. Whereas geosciences and landscape ecology have made rich use of graph theory, its use seems limited in physical geography and particularly in geomorphology. Common applications of graph theory includes analysis of connectivity, path networks, subnetworks, and network structures, network optimization, and in many engineering situations. In terms of future outlook, graph theory has enormous applications, and I believe that as we progress within the field, it will be used more and more frequently for simulations and representing models and networks and so on and so forth, especially in the field of computer science. There have even been some libraries developed to work with graph theory, including the Python library NetworkX. As more research is done, I hope more and more problems will hopefully be solved. One of the more interesting developments that have been recently developed in graph theory is in relation to cryptocurrency, in particular cryptocurrency transactions. The Lightning Network is a network composed of nodes and payment channels, aka edges, And they're strictly made up of two end nodes, which by sending an initial amount to the payment channel is what allows for extremely fast Bitcoin transactions between both connecting nodes. In order to join the Lightning Network, a node needs to have a minimum of at least one payment channel open with another node. Nodes and payment channels, as introduced above, combine for a classic example of a graph-like structure. Once a payment channel is open, both users can send transactions back and forth endlessly in both directions, which means that Lightning Network represents an undirected graph, which we had mentioned earlier above. But in this case, it has quite a large application in the transaction of cryptocurrencies. Overall, graph theory has a wide range of applications in a multitude of fields like math and computer science, and it is really amazing to see how such a simple notion of a graph can have such significant impacts. And these here are my references, and that's the end of the presentation.